All right. Um, okay, let's take a look. So on Monday, we talked about maximum likelihood estimation, and we estimated the what do you call it? The W vector, which contains, our slope and intercept, or whatever coefficients that we're looking for. And this time, I wanted to do maximum likelihood estimation of the variance term. So our model assumes that the random noise that's in our data is normally distributed. Okay. And so um, we uh, we saw this, but this is basically the normal PDF where we're just taking the difference between our actual value and the expected value, and we're taking the product of all of these normal densities. Okay, and in here we have a sigma term for our um, our standard deviation, or sigma squared for variance. Okay, and we said um, that if we are trying to maximize the likelihood function with respect to the weight matrix, because we're trying to maximize this. Okay, and when we take the log of this, we see, and there's a negative here. We can see that maximizing the likelihood is equivalent to minimizing the this term right here, which is equivalent to the sum of squared errors. These are all constants over here. So because this is multiplied by a negative, what we want to do is we want to minimize this so that we can maximize. And that's equivalent to maximizing our likelihood and our log likelihood. Okay, and when you do that, we find our our W vector, the best estimate that's going to maximize our likelihood, is going to be the same as the solution that minimizes the sum of squared errors, and that's x transpose x inverse x transpose t. Okay, so now what we want to do is take the likelihood function, and now we want to maximize it with respect to sigma. Okay, so I'm going to start off with the same likelihood function, or the same log likelihood function, and we have all of this. And what we're going to do is we're going to take the derivative of this with respect to sigma. Okay, and so there's no sigma term here, so this zeroes out. We have n log sigma. The derivative with respect to sigma is going to be n over sigma. And then we got negative 1/2 sigma squared, and that's going to become um, 1 over sigma cubed. Okay. And the negative cancels out here because it's sigma to the -2. And that cancels out with the basically the negative 1/2. And then we have all of this. Okay. We are going to set our derivative equal to 0 and then solve for sigma. So doing that, I'll add sigma to both sides. Or add n over sigma to both sides. We get n over sigma is equal to 1 over sigma cubed here. Multiply both sides by sigma cubed. And on the left, we will get sigma squared. And if I divide both sides by n, on the right, I'll get 1 over n, this. And so this is going to be the term of sigma squared that minimizes or maximizes our likelihood, or at least where our derivative is equal to 0. We get 1 over n, the sum basically of our squared errors. So we have is our mean squared error. 1 over n is times our sum of squared errors here. Okay. And so this, so we can see that the maximum likelihood estimate of our variance turns out to be the mean squared error. Um, and then what we can do is we can plug that back in. Okay, we can plug our estimate of sigma squared back into the log likelihood, and we can see, what is the log likelihood at the maximum. So our log likelihood is this, and I'm going to plug in our estimate of sigma squared there. Okay, and so knowing that sigma squared is equal to this, okay, um, basically I can replace all of this right here, our sum of squared errors, with n times sigma hat squared. Okay, so we're basically estimating all of this, plugging in sigma hat squared, replacing this is equivalent to basically doing 1/2 of the log there. So that's how we go from n log sigma to n over 2 log sigma squared. Okay. And then because we've got our estimates of sigma squared here, they cancel out. And so I can kind of rearrange and combine terms. And this is going to be our log likelihood. And we get 1 plus log 2 pi. This is just a constant over here. But over here, the log likelihood of our model is at the maximum, it's going to be have this term, okay? Negative n over 2 log sigma squared. Okay, and so looking at this log likelihood, we can see that because there's a negative constant in front of this, okay, the log likelihood is going to get bigger if sigma squared gets smaller and smaller. Okay, so these are all constants over here, but if we're trying to say we want to have a log likelihood, maximize the likelihood of our model, we would want to have as small of a variance term as possible. Okay, and so this sigma squared, that's the variance of the error in our model. And when we think about what is the error in our model, that's basically the leftover variation after our model makes a prediction, right? So it's how much, how different are our predicted values, or how different are the actual values from our predicted values, okay? And so if we want to shrink the error to be as small as possible, the ideal situation would be to basically overfit the data. Okay, if that is our only goal, is to shrink the kind of the leftover error, because remember sigma squared, our estimate of sigma squared is basically the mean squared error here. And so if we want to just shrink this to be as small as possible, we basically overfit the data so that our W times XN gets as close to our actual values TN as possible. Okay. But we know that making your model as complicated as possible just to kind of maximize the likelihood is not a good idea, just because that's going to overfit your data. Okay. All right. So that's what we have here regarding our maximum likelihood estimation for our variance term. Okay, let me go ahead and give you our first view quiz answer. And today that is the letter A. Put that in the... Okay. I want to keep talking, and I want to bring up Fisher information. So Fisher information, is another important concept. And again, there's a lot of overlap with what I'm covering now with say 100C, but I don't know. Some of you have taken 100C and some of you haven't, and maybe some of you are taking it right now. But anyway, I just want to kind of make sure we cover this, and I think it's okay if there's some overlap if you've seen some of this stuff before. Okay, so just a quick review. The derivative of function tells us the rate of change of the function, and it's equal to the slope of the line tangent to the function at that location. And then the second derivative tells us how quickly that slope changes, and it tells us about the curvature of the function. And so if you have a large slope, if you have a large second derivative, okay, that means the slope changes rapidly, right? And so that would indicate you have a kind of a sharp bend or a sharp, the slope changes rapidly at that location. And then the sign of the second derivative tells us about the concavity of the function. And so if you have a positive second derivative, it means you're kind of going from like negative to positive, and so you have it's concave up, and the location there at x is going to be a local minimum if you have the derivative equal to 0. If the first derivative is equal to 0, and then the second derivative is negative, then that means it's going from kind of a positive slope to a negative slope. And so that's concave down, and then x would correspond to a local maximum. If your second derivative is equal to 0, then we don't know the concavity. X could be an inflection point. It could be a saddle point. We're not quite sure what's going on with the second derivative there. Okay. And then so if we extend this to the multivariate generalization, the gradient, okay, then the input to our function is going to be this vector. And then if we take the gradient of the function with respect to that vector, then we get a vector itself. And basically the components of that vector are all partial derivatives with respect to each of the components. So the gradient with respect to w is basically going to be the partial derivative of f with respect to w1, partial derivative of f with respect to w2, and so on and so forth. And we can kind of think of the gradient as the multivariate generalization of the derivative. Okay. And then, so this would be kind of our, the generalization of the first derivative. And then we can think about, okay, what about the second derivative? Okay. So if all of the second partial derivatives of f are continuous, then we end up with the Hessian matrix, okay? And we are going to have an n by n matrix of partial derivatives. So basically, you can think of taking each component here and then taking the gradient, like, so here's the gradient, basically our first derivative. This is the partial of f with respect to w1. And then you can think of saying, okay, well, what if I want to take the gradient of each component here, okay? And then so I would have basically a partial derivative of this with respect to w1, partial derivative of this with respect to w2. And so therefore, when you fill out the Hessian matrix, you basically have the second derivative with respect to w1. And then here you get basically we have the partial derivative of f with respect to w1, and then we're going to take the derivative of that, partial derivative of that with respect to w2. And so you get d2f of dw2, dw1, and so on and so forth. and then we would take the partial of this with respect to w sub n, and we get this. Okay, and you can imagine doing this for each of the components, and so we end up getting this square n by n matrix, where the diagonals is going to be basically d2f dw1 squared, and then we have d2f dw2 squared, and so on and so forth. So this is kind of the idea of if you take the second derivative and if you bring it to the multivariate version. Okay, so this is called the Hessian matrix. Okay, and so if we think back to the univariate function, the sign of the second derivative tells us about the concavity of a function. Okay, whether it was concave up or concave down. And if we have a multivariate function, we have a similar idea here, and we can learn about kind of the curvature. And this depends on the definiteness of the matrix. Okay, and so a matrix can be positive definite or negative definite, and that means so if a matrix is positive definite, if when you calculate all of the eigenvalues of the matrix, all of the eigenvalues are positive. Okay, so if you have a positive definite Hessian matrix, okay, then that means the function is concave up. You can think of a bowl that is with a minimum at the bottom. Okay, and so so if you calculate the gradient of a function and it's equal to 0, I should say a vector of zeros at some point x, and if the Hessian matrix is positive definite, then it corresponds to a local minimum. If you have a negative definite, then the function is concave down, and you can kind of think of a hill, and your x is going to be located at a local maximum. Okay. If you have both positive and negative eigenvalues, then it's basically positive in one direction and negative in another direction, and that would correspond to like a saddle point. Okay, so you can kind of think of kind of like a saddle where like on the horse on one side it's the maximum on the horse, but then in the other direction it forms upwards, so it kind of the person sitting on the saddle fits fits nicely there, I guess. But so it's concave up in one direction, concave down in another direction. And then if you do have eigenvalues that are equal to 0, so you have like a semi-definite, positive semi-definite or negative semi-definite or something, then that means, we would need some more information to determine concavity. Okay. The Hessian matrix, these are just some additional properties. This is equivalent to the Jacobian matrix. So, the Jacobian is basically, the matrix of second derivatives and things like that. Okay. The Hessian matrix is, I put here, usually symmetric. Okay. Maybe more formal would be, is symmetric under regularity conditions, certain, and basically it requires the second, it's going to be continuous if the second, it's going to be symmetric if the second derivatives are continuous. Okay. And then there's a theorem, Schwarz's theorem, and that is if the second derivatives indeed are continuous, then the order of differentiation doesn't matter. So basically, when you have the second derivative, dw2 dw1, it's equivalent to dw1 dw2, and that would make this term and this term equal, and then therefore this entire matrix would be symmetric because the order in which you do the derivation, whether it's W2 first, W1 first and then W2, or W2 first and then W1, the order doesn't matter, and therefore it's going to be symmetric. Okay, so we could think of the Hessian matrix, okay, as something that informs us about the curvature of the function, okay, because kind of like the second derivative tells us how rapidly the slope changes, the Hessian matrix, which is kind of our multivariate equivalent of the second derivative, will tell us about the curvature, okay? And so if we apply it to the likelihood function, or our log likelihood function, we get an idea of the curvature of the function, and that will tell us how confident we can be in our parameter estimates, okay? So that feels a little bit strange. Curvature, the curvature of the function will tell us how confident we are in our parameter estimates. So I just want to run through a quick demonstration of this idea of how the second derivative tells us about how confident we are in our parameter estimates. And then I'm going to start off with the univariate case here. Okay. So let's imagine we have a pouch, and inside our pouch, we have red marbles and blue marbles. Okay. And the proportion that is red is a fixed value in our pouch, but we just don't know what it is. And so we're going to try to estimate what the proportion red is by taking observations. And let's say we draw 10 marbles with replacement, and we get red marbles 4 times. And so if we calculate the likelihood of our observed data, we would have theta to the 4th and 1 minus theta to the 6th. Basically, we saw red 4 times and blue 6 times. And if you plot the likelihood of this function, it looks like this, okay? Where the maximum of our likelihood is at 0.4, okay? So this is our likelihood function after 10 draws with replacement, and we saw 4 red. And so we could say, oh yeah, the likelihood function is maximized when theta is 0.4. It's also got, because we only observed 10 observations, it's possible for theta to be, like 0.6, or, even 0.7 is not completely out of the realm of possibility. It's, we'd be surprised, but it's also, still possible. And, meanwhile, 0.2 and, 0.15 is possible. 0.1, probably not as much, but, there's kind of a range of values that we say, well, theta could be. So the likelihood function shows us that 0.4 is going to be the value of theta that maximizes the likelihood, and that makes intuitive sense. But it says, any value basically between 0.3 and 0.5 is also very likely, but there's a bunch of other values that still have high likelihoods. Okay, if we do the same thing, but this time I've gathered a lot more data. Let's say I've drawn 1,000 marbles with replacement from the same pouch, and now I observed red 400 times out of 1,000. Okay, what does their function look like then? Okay, the likelihood is going to be theta to the 400, 1 minus theta to the 600. And if I plot that, this is what my likelihood function looks like now. And so, it's still maximized at 0.4. But now, because I've observed so many observations, the likelihood says, yeah, you know what? 0.5 doesn't make sense. 0.6 doesn't make sense. The only values that really make sense would be 0.4, maybe 0.41, maybe 0.39, and things like that. Okay. So if you compare this plot with this plot, they both have the maximum at 0.4, but this one is a lot more, we would say pointy, right? Okay. And so this kind of pointy or the high curvature tells us that only values that are close to 0.4, like 0.39 or 0.41, still have high likelihood. Okay. And, what's the likelihood that theta is 0.3? Basically zero. What's the likelihood that theta is 0.5? Basically zero. Okay. And so we would say there's much less variance as far as what theta could be. Okay. So if we think about the second derivative of these log likelihood functions, okay, so if I take the likelihood function, I take the log of this, I get 4 log theta, 6 log 1 minus theta. And then the second derivative looks like this. And here it is for the 1,000 draws, the likelihood thing. It's basically the same thing, except instead of theta to the fourth, I have theta to the 400. So I'm going to get 400 times log theta and 600 times log 1 minus theta. And so the second derivative of this draw, of 1,000 draws, is the same thing, except it's multiplied by 100, right? Instead of -4 over sigma squared, I got -400 over sigma squared. And instead of -6, I have -600 over 1 minus sigma squared. Okay. And so this second derivative is just basically much bigger, 100 times bigger. Okay. And so let's say I plugged in theta equal to 0.4, this is going to maximize the likelihood, the log likelihood here. Okay. And so my second derivative at 0.4 is -41.667 when we deal with the 10 draws. And if I plug it in for the 1,000 draws, it's -4,166.7. Okay. And this reflects the curvature of the function. Okay. The sample with 1,000 has much higher curvature. Okay. The slope changes rapidly. Okay. So our second derivative tells us how fast the slope changes, and that the slope changes rapidly. It goes from very high positive slope, okay, so very kind of steep upward slope, and then it rapidly becomes very steep downward. Okay, so it goes from positive to negative very quickly. Whereas back here, we have positive slope and then negative slope, but that change is a lot more gradual. Okay, it goes from kind of a medium positive, and then it becomes more shallow until it becomes zero, and then it starts to become more negative, and we get negative slope. Okay, so the second derivative of this is kind of a lot more, is a lot smaller, because the rate of change on the first derivative, the rate of change on the slope is a lot slower. Okay. So we can kind of think of that curvature, or basically how pointy that graph is, reflects that, we have less curvature there. So, the fact that the likelihood function has much more curvature, meaning the slope changes rapidly, tells us that we have, a lot more information regarding where that value of theta is. Okay. And that makes intuitive sense, because if you think about how much information do you get when you only have 10 data points versus how much information do you have when you have 1,000 data points, you have a lot more information after 1,000 data points. Okay. And so this relationship between the curvature of the likelihood function, basically how quickly the slope of the likelihood function changes, okay, and the information we have about the parameters, basically, when it changes rapidly, we can be confident that theta is, really close to 0.4, versus over here, theta, the likelihood is maximized at theta equal to 0.4, but it could be, much higher, much lower, that relationship is tied together in Fisher information. Okay, let me give you your second view quiz answer. And that's going to be E. E as an elephant is our second view quiz answer. Okay, so there's different definitions for the Fisher information, okay? But, we can think of the Fisher information as a way for us to kind of measure the information a random variable can provide about some unknown parameter, okay? The formal definition of the Fisher information is that it is the variance of the score, and then the score is the derivative or the gradient of the log likelihood, okay? So, here we have the likelihood function itself, but, we could say, okay, well, here's our log likelihood, and if we take the derivative of the log likelihood, we have this, and then what is the variance of this, okay? That is the official definition of the Fisher information, okay? If the log likelihood is twice differentiable with respect to our unknown parameter theta, then the Fisher information is also equal to the negative of the expected value of the second derivative, okay? So if you think about, all right, what is the second derivative of the log likelihood? And what is the expected value of that second derivative? The Fisher information is the negative of that, okay? And we'll use this definition to kind of learn a little bit more about the Fisher information. So here I'm going to say the Fisher information, which is indicated by using, kind of fancy I of theta, the Fisher information of our unknown parameter theta. This is going to be the negative expected value of the second derivative of the log likelihood, okay? Okay. This thing here, this negative expected value, I'm going to put in this term right here to indicate this is our probability function f, okay, of a random variable x given some parameter theta, okay? And so this is going to be, this is the expected value taken with respect to the random variable. So we're not taking the expected value with respect to the parameter theta, but we're taking the expected value with respect to the random variable, okay? And the distribution of that random variable is defined by, the function, which uses theta as part of its function definition. So we're taking these expected value with respect to the random variable. Okay, so if we look at a single Bernoulli observation, okay, then this is going to be our Fisher information. So I've got the negative expected value of our second derivative of the log likelihood of our function, okay? So for a single Bernoulli observation, our probability mass function is theta to the x, 1 minus theta to the 1 minus x. And we're going to take the log of that, and that will split that up into basically log theta to the x and log of 1 minus theta to the 1 minus x, and we want the second derivative of this thing, okay? So still I haven't taken the second derivative yet, but this will become x log theta, and then I got 1 minus x log 1 minus theta. And then now I'll take the first derivative. First derivative is going to be x over theta, and over here I'm going to have negative 1 minus x over 1 minus theta. So I've got this, and then I'll take the second derivative, and this will give me negative x over theta squared. And then over here I get negative 1 minus x over 1 minus theta quantity squared. Okay. And so if I say, okay, what is the negative expected value of this? I will get basically the expected value of x, and then I'll get the expected value of 1 minus x, get the expected value of x over theta squared, and expected value of 1 minus x over 1 minus theta squared. And if we say, okay, well, what is the expected value of x, a Bernoulli random variable, then the expected value of x is theta. And so the expected value of x is going to be theta. Expected value of 1 minus x is going to be 1 minus theta. And so we're going to get 1 over theta plus 1 over 1 minus theta. And I can combine these terms and I'll get, 1 minus theta plus theta over theta times 1 minus theta. And basically the minus theta and the plus theta cancel out. And so I get 1 over theta times 1 minus theta. So this is the Fisher information from a single Bernoulli observation. Okay. And basically we'll say, depending on what theta is, the most information we can get about, the parameter theta is going to be this term. Okay, if we have n observations, okay, and we can kind of go through all of this, and you'll have basically the product of n of these things, okay, then you'll just have basically n times log of all of this, okay, and the Fisher information is basically going to all add up, and you'll end up with n over theta times 1 minus theta. So Fisher information is additive. And so if you have n observations, your Fisher information is going to be this. Okay. And that aligns with, what we had back here. Okay. With 10 observations, I got this. And with 1,000 observations, I had this. It was much bigger. Basically, if you think about what a single observation would be like 4.667, 4.1667. With 10 observations, we're basically multiplying it by 10. And with 1,000, we're multiplying it by 1,000. And so this all aligns with what we've seen. Okay, so that kind of reflects our understanding of how the second derivative reflects the curvature, and it's all kind of encapsulated with the Fisher information. So we can now move back to the multivariate setting with the Hessian matrix, okay? And so the Fisher information for a multivariate function is going to be a Fisher information matrix, okay? This is going to tell us how much information our data provides about the unknown parameters theta. And again, if the log likelihood function is twice differentiable, then the Fisher information is the negative expected value of the matrix of second derivatives, or the negative expected value of the Hessian matrix of the log likelihood. And so now I want to get the negative expected value with respect to our random variable x of basically our matrix of second derivatives, or our Hessian matrix. And we'll get basically a big Fisher information matrix. So if we do this for linear regression, okay, our log likelihood function, is going to be the product of a whole bunch of normal densities. And we want the Hessian matrix of this, log likelihood here. Okay, and then we want to take the negative expected value with respect to our values, our random variable here, which is going to be basically t, which is centered at w times x. Okay, t is our actual observations. Okay, so if I expand all of this out, okay, my log likelihood is equal to this. And then if I do the first derivative of the log likelihood, I'm kind of skipping over this because we've seen all of this already. Our first derivative of the log likelihood with respect to w is going to equal this, okay? And then we're going to take the second derivative of the log likelihood, okay? So the derivative of this thing with respect to w, okay, this is going to zero out. There's no w term here. And then the second derivative here this is a square matrix, X transpose X. And so I'm going to just get this term over here. So I'm going to get 1 over sigma squared X transpose X. This is going to be the basically our equivalent to our Hessian matrix, where we've taken basically the kind of the second second derivative equivalent of our log likelihood function, right? We found the gradient, and then if I take the kind of the Jacobian of this, or get the Hessian matrix of our log likelihood, this is what we get. Okay, so this is the Hessian matrix of the log likelihood, negative 1 over sigma squared X transpose X. And we want to know, okay, what is the Fisher information? Okay, and that's going to be equal to the negative expected value of this matrix. And so we want to know, okay, what is the and we're saying, okay, what is the expected value? We would have to do some calculations, because we're trying to find if there was a t, okay, but there's no t in here, okay, because our outcome variable is our observed values, t sub n. T sub n is normally distributed around here, and so with respect to kind of x, or with respect to t, x is a constant, okay? And so therefore, the negative expected value of this is just going to be 1 over sigma squared X transpose X, okay? These are basically constants when, we're taking the expected value of t. We're not taking the expected value of, say, X or whatever, because in our case, X being our input values, these are constants, okay? X, we're accustomed to seeing X as a random variable, but X is not a random variable. These are kind of our input, our matrix of predictor values. And we're assuming our observed values are normally distributed around W times X, normally distributed with some variance sigma, okay? And so so X is a constant if we're thinking about the expected value of t. So our negative expected value of our Hessian matrix is going to be 1 over sigma squared X transpose X. And so this is how we can kind of interpret all of this, okay? So our model is that W times X is going to give us kind of the true mean, okay? W is going to represent the true set of parameter weights in the population. And our model is that there's a true kind of mean value that we can get by doing W times X. And it's just that our observed values, T or Y or whatever we want to call it, are, just have some random noise in it, okay? So sigma squared is the amount of variance that we have in this noise parameter. And so if we have lots of noise, okay, if this sigma squared is big, then we have less information, okay? The Fisher information is small, and we're going to have less confidence in our estimates of W, okay? If there is little noise, okay, if sigma squared is big, then the Fisher information is large, and we'll have more confidence in our estimates of W, okay? So that's what we have, okay? The Fisher information, an important application of that is in the Cramer-Rao lower bound. And the Cramer-Rao lower bound is a theorem that states that the variance of any unbiased estimator, okay? So if we have an estimator of the actual parameter, unbiased estimator theta hat of some actual parameter theta, is always going to be greater than or equal to the reciprocal of the Fisher information. So the variance of theta hat, the lower bound, is basically 1 over the Fisher information. And so this gives us a benchmark for kind of the best possible precision or the lowest possible variance that we can have for an unbiased estimator. And if we say, okay, well, what is the variance of our estimator W's, okay? So W is, X transpose X. inverse X transpose T. And keep in mind, T is X times W plus our noise epsilon. So I'm going to just plug that term into here. Then W, our estimates of W hat will be equal to this, and all of this X transpose X inverse X transpose E here. Okay, so I get W plus all of this here. Okay, and this term, the expected value of epsilon is 0. So this whole term right over here is going to zero out. So the expected value of W hat is just W. And so we can say W hat are, using this as a way to get our estimate of W, that's going to be unbiased. Okay. So if I want to say, okay, well, what is the variance of this? Okay. So what is the variance of W hat? So again, W hat is X transpose X inverse X transpose E. And I can say, okay, what is the variance of all of this? This is what we get. So kind of multiplying all of this out, okay, the variance of epsilon is going to be sigma squared, okay, multiplied by an identity matrix. So everything kind of the thing dimensions all line up, okay. And if you go through all of these things, a bunch of these things cancel out. The X transpose X, X's, and the X trans and inverse and things cancel out, and we're left with sigma squared times X transpose X inverse. Okay. And this is basically the inverse of our Fisher information. So our Fisher information is 1 over sigma squared X transpose X. And the variance is sigma squared X transpose X inverse. Okay. And so in our case, the variance of W hat is equal to the inverse of the Fisher information. And it is equal, because it is equal to that, that's the lower bound for what the variance can be. And so this confirms that W hat is indeed our best unbiased estimator. Okay, so that was kind of a lot. Again, a lot of overlap with say 100C. So my apologies if you've seen all of this stuff already. And if you haven't, then you might see it again in 100C. And I think it's okay to get the same stuff more than once to kind of reinforce it. It is important things. And let me go ahead and give you your last view quiz answer. Third view quiz answer today is the letter A. Okay, so with that, we'll end here. And again, appreciate your flexibility for meeting online. And we'll see you on Friday.